So now I want to look at local maximums and minimums and what this looks like on a graph and how we actually define this algebraically. So let's first look at the definition of a local maximum and a local minimum, and then we will look at a couple examples so that we can see exactly what it will look like. So a function, we'll call it f of x, has a local maximum at x is equal to c if and only if there is an open interval AB which contains C. So I have this open interval of x values that contains this one specific x value such that f of c is greater than or equal to f of x for all x in AB, so for all x that are in that open interval. So let's think about what this means. There is a particular x value, x is equal to c, such that the function value, the y coordinate, at that particular x value is greater than any other function value for any x coordinate around it. So if you look at it on a graph, you will probably see something like this. And you will get a point where you hit a maximum. All other points around it, all the other x coordinates, have a lower function value than the x coordinate at that particular point x is equal to c does. Okay, so you can always draw it out like this. And you see that f of c is greater than f of x for any other x coordinate that surrounds c. So I've got this open interval on which I do this. A local minimum is almost the same definition, it's just that f of c is less than or equal to f of x. So a local minimum is at a point x is equal to c if and only if there exists an open interval AB such that f of c is less than or equal to f of x for all x in AB. So again, we have this open interval that contains this value c, and then for all other x values that surround c, the function value this time is going to be greater than the function value at c. So if you draw that on a graph, it would look something like this, where we have x is equal to c, and you'll see that the function value here is less than the function value of any of the other points around it. If you ever have a constant portion of the graph, so let's say you had this graph but then there was a constant portion that carried on here, so you have this horizontal line. If you see this on a graph, then they are actually both maximums and minimums. So if you get this constant portion of a graph, it means that for all x values in the open interval between this point and this point, you would have a local maximum and a local minimum for a constant portion of the graph. Whenever you do this, do not include endpoints. So we'll write this all down. Constant portions are both maximums and minimums. Okay. And if you have any endpoints in your graph, they are neither local maximums or minimums. Even if they do give you that largest function value for a particular point, or the lowest function value at a particular point, you cannot count them as local maximums and minimums. A good example to look at here is f of x is equal to x squared. So it would be this quadratic curve. I'll do a quick sketch of it here. Okay, here we have this local minimum. Okay, at x is equal to 0, we have a local minimum of 0. Okay, whenever you talk about local maximums and minimums, keep in mind that you always say that the local maximum or minimum is the function value. It's the actual value found at the x coordinate. So here we have a local minimum of 0 found at x is equal to 0. So the local maximum or minimum is always the function value, it's the y value, and it is found at the x value. So whenever you do these in homeworks or anything like that, that is always how I want you to state it. It's always the function value is the actual local maximum or minimum, and it is found at the x coordinate. If instead of the graph f of x is equal to x squared, if I now had a restricted domain, so I'm just looking at f of x is equal to x squared, but I'm restricting the domain so that x is greater than or equal to 0. In this case, for this particular function, I don't have any local maximums or minimums. Okay. In this graph here, I had a local minimum of 0 found at x is equal to 0. Well, now my local minimum that I have from my first graph is now an endpoint, and endpoints cannot be counted as maximums or minimums. So in that case where we had the graph of the restricted domain of f of x is equal to x squared, we have no maximums or minimums. I now want to look at this example. Okay. I want to look at what are our maximums, what are our minimums, and then look at constant portions of the graph, etc. So our local maximum, we already have it circled here. Our local maximum is 3, and it's found at x is equal to -2. Okay, I have this maximum value here. My minimum, my local minimum is down here. So I have a local minimum is -3, and it's found at x is equal to 2. I also have another local maximum and minimum, and that is on this constant portion of the graph here. Between x is 4 and x is 5, not including those points because we do not include those end points or turning points where we now change direction, we have this constant portion of the graph that is counted as both a local maximum and a local minimum. So remember, whenever you do this, it's always on an open interval. So whenever you have multiple values for which you have this constant, make sure you put it on an open interval, because otherwise you can't have a closed interval for local maximums and minimums. So there is both a local maximum and local minimum of 0, and it's found on the interval 4, 5. So between those two x values in that open interval 4, 5, again, we don't include those two values because we need an open interval in order for the local maximum and minimum to be defined, and we don't include any end point. So we can't include that x is equal to 5 because that actually takes us to an end point. So we have both a local maximum and a local minimum of 0, and it's found on that open interval. So now I want to talk through the different graphs that you may come across before we look at translations of these graphs later on in this course. I want to make sure that you know what these basic functions look like when you graph them. First one I want to look at is the basic linear graph, so something that is y is equal to x. Okay? When y is equal to x, that means it must go through the origin, so it goes through 0, 0. And it is this straight line that goes off towards infinity and negative infinity. It is defined for all x values. It is defined for all real values. So our domain we see here is negative infinity to infinity. Our range would be all of the function values that we get whenever we plug in an x value. Well, here y is equal to x for this linear graph. So that tells me that the range, again, is all real numbers, negative infinity to infinity. If we look at where it is increasing, well, it's increasing all the way along this graph. Okay, we can see that because it rises as you go from left to right. So if we were to pick that x1 and x2 value like we did before within this open interval of negative infinity to infinity, we pick any two x values where x1 is less than x2, then we see that the function value of x1 is going to be less than the function value of x2. We can see it's not decreasing anywhere because it has this positive slope, and it has no local maximums or local minimums. Okay, because we don't include any endpoints, it is constantly increasing. There is no point where we're going to get this local maximum or local minimum. The next graph that we need to be aware of is one that we've looked at a couple times before, and that is the quadratic graph for y is equal to x squared. So we've seen this a couple times before and discussed it. We already know that its domain is all real numbers. I can plug in any x value and square it. So I know that my domain is all real values. The range, we said, was from 0 and including 0 all the way up to infinity, because whenever I square any x value, my resulting value, that function value, is always going to be a positive number, and the lowest number that I can get is 0, and that is found when I square 0. Where is it increasing? Well, it's increasing everywhere on the right of this graph. Okay, we can see that here. We can see that this whole line here, all the way up, it's increasing. Okay, and again, we don't include any endpoint where it suddenly turns and changes direction. So we do not include this value 0 down here. It's just increasing from 0 up to infinity, but not including 0, because that 0 is a turning point. Similarly, it's decreasing all the way down here from negative infinity all the way to 0. So for any x value between negative infinity and 0, this is decreasing. And again, we don't include 0 because it is a turning point. We have no local maximums. There is no point where we get a maximum, but we do get a minimum of 0, y is equal to 0, and that is found at x is equal to 0. That is a local minimum. The cubic graph, y is equal to x cubed. Again, it's defined, has a domain of all real numbers. We can always plug in any x value and we can cube it. Its range is also all real values. It's not like the quadratic graph where we square a value and it's always positive. When you cube a value, you can also get a negative value back. For example, if I cube -2, I get -8. So there, whenever you cube one of these negative numbers, you're going to get a negative number back. And your range, therefore, is going to be negative infinity to infinity, because I cube a negative value, I'm going to get a negative value back. The larger the negative value that I cube, the larger the negative cubed value I'll get back. And similarly with positive numbers, the larger the positive number that I cube, I'm going to get an even larger positive number back. So my range is going to be negative infinity to infinity. It's all real numbers. It is increasing everywhere. So all the way along here, I'm always increasing. As I go from left to right, I'm getting a larger and larger and larger function value out. Even though it looks like it flattens off slightly here, I am still increasing the whole way along. It doesn't actually change direction. It just slows and then gets steeper and steeper and steeper again. Obviously, I'm not decreasing anywhere here. I don't have any local maximums. I don't have any local minimums. There is no point where I change direction in order to get one of those local maximums or minimums. Then I have the basic square root graph. So this is where y is equal to the square root of x. I can't square root a negative number. So my domain is from 0 to infinity. I can square root 0 and get 0. So I'm going to include 0 in my domain and go all the way to infinity. But because I can't square root any negative number, I start at 0 and go up to infinity. The range, again, I'm always going to get a positive number back when I square root because I'm only looking at the positive square root here. Okay, whenever we square root a number, we normally either say that we've got the positive or negative square root. But here I'm just taking the positive square root. I'm not worrying about the negative square root because that would actually give me 2 y values for every x value. So I'm only worrying about the positive square root here in order to actually give me a function to graph, because if I worried about the negative value too, then I wouldn't actually have a function. But right now, I'm just looking at the positive square root, meaning that my range is from 0 to infinity, including that 0 value. I am increasing everywhere from 0 to infinity, but I don't include that endpoint of 0. Remember, we never include an endpoint. It's an open interval that we always increase or decrease on. So I'm not going to include 0. I'm going from 0 to infinity, not including that endpoint. I'm not decreasing for any x values. There is no x value for which I'm decreasing on this graph. And I have no local maximums or minimums because, again, even though it looks like 0 is the smallest value I get, which is true, it's the smallest y value I get for any given x value, I don't include endpoints for local maximums or minimums. Next, I'm going to look at the cube root graph. So y is equal to the cube root of x. What does that look like? And this is the graph that we get. Its domain is all real numbers. I can cube root negative and positive numbers. So my domain is all real numbers. Similarly, I can cube root any real number. So I can take the cube root of, let's say, -8 and get -2. So I've got a range of negative infinity to infinity. I'm increasing everywhere. I get steeper and steeper and steeper as I get closer to 0, but I'm not changing direction. I'm always increasing, even though sometimes it looks like it's steeper or flattens out. I'm always increasing across my whole range from negative infinity to infinity. I'm not decreasing anywhere, and I have no local maximums or minimums because I have nowhere where I change direction. Then we have the absolute value graph. Y is equal to the absolute value of x. That means for any x value, positive or negative, I make it positive. So for example, the absolute value of -3 would be 3. That's what this means. I'm taking the absolute value of it, I'm making it positive. So my domain is all real numbers because I can take the absolute value of positive or negative numbers. My range is going to be all positive numbers starting at 0. The absolute value of 0 is 0. The absolute value of any negative number is its positive counterpart, and the absolute value of a positive number is still that same number. So my range is going to be 0 to infinity, including 0. I'm increasing along this line here on the right of the graph, and I'm decreasing here on the left of the graph. That means that I'm increasing from 0 to infinity, not including 0, because 0 is a turning point, and I'm decreasing everywhere from negative infinity to 0, so from x is negative infinity to x is 0, but again, I don't include x is 0 because it is a turning point. So I always use open intervals for increasing and decreasing. I don't have any local maximums, but I do have a local minimum. I have this local minimum of y is equal to 0, and that is found at x is equal to 0. It is one of those turning points. It is a local minimum. And finally, we have the basic reciprocal graph. That is where I take a value and then I find its reciprocal. So for example, if I took x is equal to 2, its reciprocal would be 1/2. Okay. I cannot have the reciprocal of x is equal to 0 because that would mean that I would be doing 1 divided by 0. That doesn't work. So my domain is all real numbers, not including 0. So here they have written it in set notation as negative infinity up to 0, not including 0, and then union 0 up to infinity, again not including 0. You could also write it as all real numbers, not including the 0 value, using set brackets. My range, I can get any real value I want back from this apart from 0. There is no way for any value of x that I can make that work. Okay, if y was equal to 0, so my function value 0 was in my range, that would mean that I could get a value of y of 0. There is nowhere where 1 over something equals 0. Okay, so 0 is not in my range, but I can get any other value of y that I want. For example, if I wanted a y value of 3, I can get that by doing 1 divided by 1 over 3. That gives me 3. So if I took an x value of a third, I could get a y value back of 3. So I can get any real number back that I want, and any y value is in my range except for 0. 0 cannot be in my range. It is not increasing anywhere. Nowhere on this graph are you increasing, because as we go from left to right for both parts of this graph, as we go from left to right, we are actually dropping. So as I go from left to right, I'm decreasing. As I go from left to right, my graph falls for both of these. So I'm not increasing anywhere, I'm decreasing everywhere where this is defined. So for all x values of negative infinity up to 0, not including 0, and everywhere from 0 up to infinity, for all of those x values, I am decreasing. And there is nowhere where I have a local maximum or local minimum, because there is nowhere where I change direction. So these are the basic graphs that you need to know, and we're going to work on translating them later in this course, where we add certain things to them, we multiply them by certain things, etc. And we'll look at transforming them by stretching them and shrinking them and moving them up and down and left to right. So make sure that you know what these graphs look like, so when we come to this later in the course, you already have these committed to memory.